received her PhD in mathematics from Vanderbilt University and worked as the assistant research professor at Johns Hopkins. Professor Tang is interested in employing and developing techniques in statistical learning, harmonic analysis, approximation theory, probability to solve problems in interface of machine learning, inverse problems, signal processing, and dynamic systems. So, Sui, please.
Oh, thanks a lot for your nice introduction and the invitation. It's really a great pleasure for me to have this opportunity to speak, to talk about my recent work. So today I'm going to actually present the data-driven discovery of interacting particle system using Gaussian process. So I would like to acknowledge the support, funding support from NSF and Santa Barbara, as well as the psychological support, by the curiosity to understand the natural phenomena. Like here is the shape of the birds, of flocking birds. Okay, so and below is a long list of my collaborators. When I was at Johns Hopkins, I was very fortunate to meet them and we work together. And so I will present also a part of work relevant to them. And for the work with Gaussian process, I work with Jinchao Feng, who is currently at Johns Hopkins, as well as Yunxiang Ren, who is at Harvard. So recently, due to the impressive advancement of data information technology, we have a lot of data actually collected from satellite, GPS sensors, and many data actually are dynamic. And this inspired a lot of research in data-driven discovery of dynamic systems. And here I just gave a few examples, such as understand cognition from neural recordings to actually infer the climate pattern from weather data. And maybe you heard about data assimilation problem. And recently there's a lot of work actually to extract information from COVID-19 data, and for example, to make the prevention policy. To address these critical questions, and one of the fundamental tasks is to extract governing equations or laws from data. So in this way, we can actually give a fundamental interpretation about the dynamic system, make predictions on the future events, and we simulated the dynamics on totally unseen data sets. And on the right-hand side, actually, I take a very cute example from the calculus book. So in the calculus book, there's a homework problem, like how to derive the governing equation for the single pendulum. And we have a very well understanding about the system, and it so as to know some unknown parameters in the system, and together with the measurement data, very accurate one from the book, we are able to write down the governing equation. However, this is not the case in practice, and we typically have a high dimension system, so we are going to face the curse of dimensionality. So in a minute, I will say why. And we typically have limited physical intuition knowledge, and we don't know what's the typical way to actually model dynamic data. And the data are complicated, and it may be noise. And so they're also in practical scenarios, they have data from the videos, images. So this actually actually impose a lot of challenges in this problem. But below, I'm really going to formulate the problem in a very basic setting, very ideal setting. Even in this case, you can see that why mathematically this problem is difficult to solve. So here, let's focus on first order governing equation. So we have x dot t equal to fxt. I want to model the dynamic data. And even we give very ideal data like x, this is a position at TL, this is velocity at TL. And say we observe I have a fixed time window, 0 to capital T. And here we use this assumption to run to say the data can be collected from multiple sources. Like here, the initial conditions say random with respect to some initial probability measure. And you collect this data, you want to actually construct f hat that is close to f. So this is a velocity field for this dynamic system. First of all, if we don't have any randomness in the data, so this is an approximation problem. So if capital D is large, this is a like a well-known difficult problem caused by dimensionality. Think about you have capital D equal to 5 or 6, and you are trying to approximate this function f, say defined on a unit cube, and you choose the subunit, you partition the unit cube with a cube with the length 0.01. Even in capital D to 5, you need to 10 to the 10 in the cubes, subunit cubes to approximate it. So it's a high dimension optimization problem. And a lot of times we do have randomness in the data, and this becomes more in the statistical setting. And for example, one can model the random initial conditions. Sometimes the observations are corrupted by noise. So you have random effects in the data set. So in this case, one can actually tackle this problem from the regression point of view. And if we don't have any knowledge about this f, and then this is a function defined on RD, actually in the non-parametric regression, the theory is well established. You can see from the classical theory, suppose this f satisfies some smoothness condition. They say this alpha hold regular. And so this n is the number of samples you need to take in order to approximate f well. So you can see the rate here is n to the negative alpha over 2 alpha plus capital D. So D is ambient dimension. So if D is large, you need to a lot of samples. So this going to be very computationally expensive. And so back to the ODE setting, we do have dependence in the data. So this rate still would be unsatisfactory if capital D is large. So to summarize, if we want to do the data-driven discovery from the scratch, it's going to be challenging problems. Fortunately, in a lot of scenarios, people have different prior information about the dynamic systems, and there has been a lot of research actually employing ideas from regression based on the machine learning and to tackle the problems in various settings. And this is definitely a non-exhaustive list. And for example, people want to figure out do the parameter estimation. And here, I also want to mention the work to the sparse regression. So assume this F is sparse with respect to a large dictionary, and the people use the idea from the model selection from sparse regression to find the few active items can represent the dynamics. And also, there's a lot of work using the expressive power of neural networks to tackle the high dimensionality. And there's also work in symbolic regression and a Gaussian process regression. And there's a lot of empirical advancement in the field, but still, there are a lot of open mathematical questions and also computational challenge. And from the inverse point of view, what's the identifiability for the targeted problem, and how to understand the methodology, why it works, why it fails, and how could you generalize your methodology to tackle other systems. And also another one is the scalability. Okay, so I'm not going to actually talk about the very generic dynamic systems. And here I would like to, you are sharing Keynote. Can you see my screen now?
Not exactly. It's white. Everything's white for me.
Oh, okay. I think somehow I click on this thing. Let me actually do it again. So sorry for this technical
No worry about
difficulty. Okay, so yeah, now I think okay, great. So I'm going to focus on the agent-based systems. So agent-based systems are common dynamic systems, often in our real world. Below I show actually 4 examples. You can see the range from the planet systems to animal groups. So the agents can refer to planets and fish, birds and sheep. And so you can see in these animations, actually in these systems and the agents or particles, sometimes called them particles, they interact and display a rich variety of collective behaviors. And the non-standing science problems are trying to find the individual interaction rule that can explain the collective behavior. The relevant research can go back to the time of Kepler and Newton, when they actually collect the very accurate the planetary motion data and try to understand the interaction rule. And this those as grand challenges in science. And polymath community, people want to derive the governing equations actually to explain this collective behavior. And they inspired a lot of, inspired from physics. Actually, people use the mechanical system to try to explain the collective behavior of this agent system in other disciplines. And below, I actually present a very general system. And here we have n agents, let's say in RD, and with masses m1 to mn. So the form of the governing equation here is derived from the Newton's second law. And you can tell this is mass time acceleration. On the right-hand side, we have the friction force, is denoted by F. And later I will give more explanation. And this part is the interaction force. So it's the derivative of energy function, only depends on pairwise distance. So this actually encode the translation symmetry and permutation symmetry, and as well as rotation symmetry. Is a simplification of the real world model. And here we call this phi. Actually, it determines the pairwise interaction. So you can see that here people make assumption that the interaction only depends on the pairwise distance. So this type of like dynamic systems have found a lot of applications. For example, in the opinion dynamics, back to actually 1970s, and this is called a Taylor model. So you can see in the friction force here, this alpha actually represents this pi is the bias of the agent. If the agent is stubborn with the bias pi, this kappa actually control the rate actually to converge to this bias, and the phi is the interaction. So from here you can see you typically this f and also phi has some physical interpretation. And another example, okay, so here is also kind of the trajectory given by the system in the model. So here you have three stubborn agents. One is two extreme agents and one neuron agent. So you can model like how people's opinion change over time, and they will display clustering behavior. And here another famous model is called the Dawson model. And here this is a friction force. And by tuning the parameters in the system, actually it can display a lot of like collective behaviors. And below I actually show only 3 of them. So it can be single mirror, double mirror, and a ring. And so here actually this kind of system have a lot of applications in particle dynamics, in physics, and opinion dynamics, like to model clustering behavior, and as well as in biological ecology modeling. So this is only for the homogeneous system. We only have one species in the system. And of course, you can do various extension, like you have more complicated model, like you do heterogeneous system with multiple interaction potentials. And here is a microscopic model, to describe system with small size. If N is really big and people didn't concern about the individual behavior anymore, like they use a mean field equation is a PDE model to describe the evolution of the agents. And people also use stochastic version of this kind of system to model the random effects coming from the environment. So this and the challenge is that actually even we have the formal governing equation, and the interaction kernels and the governing equation in many biological and ecological and social systems are still less well understood. There's a lot of research actually has been done in the direction forward the problem. People are interested in performing the qualitative study, like to prove and which conditions on this interaction kernel as well as initial condition, such that the asymptotic behavior to the solutions to the dynamic system can reproduce the patterns observed in reality. And also there's a lot of work on numerical simulations to demonstrate the expressive power of this kind of system. Here is a very nice review article almost 10 years ago. Still, this is a current very active research. And compared to the literature in the forward problem, and there's a little bit, there's a like scarce literature in the direction of inverse problem. And here I list 2 of them. I actually do using this type of system for the scientific discovery. typically you have the data, and it's a real data problem. And so people want to use some dictionary to model this interaction kernel. And this proceeds a dictionary, and usually chosen according to the domain knowledge of the scientist. And then they do data fitting and find a coefficient C. Typically, the goal in this kind of research is to explain the phenomena in a qualitative way, not a scientific way. So our research is actually motivated by this problem. So we studied the statistical inverse problem in the setting. Suppose the problem is that we have the data generated from system. We want to conduct a fundamental study whether we can learn this phi and even this alpha from the data generated from the system. And this is we have a specific model. We are particularly interested in the learning approach that incorporate the physical prior in the system, and we want to test whether this learning approach work, and we want to develop a rigorous quantitative analysis to address the identifiability problem, to treat it as an inverse problem and do error analysis, and trying to say what's the benefit of incorporating these physical constraints? Do they have scalability? So this is kind of our outline. So here, let me actually give a mathematical formulation to this problem. So we have actually a dynamic system. We know the form of the Gaussian equation, but we don't know the parameters here. One is alpha, and we know the parametric form of f, but we don't know the strings of f. So, and also we don't know the kernel, this interaction kernel phi. And we do have a training data set, and here is noisy observations of this position, velocity, and some acceleration. And here to simplify the problem, they say, yeah, it's on the uniform time instance, but it's not necessary. And here to model the randomness, we take the initial conditions randomly sampled from some probability measures. And here we put some Gaussian noise here on the acceleration. So this is to model the random effect imposed by the environment, as well as a measurement error, taking on the non-interaction force. So this is also for the purpose of testing the robustness of the method and also for the theoretical understanding. So the learning problem is that now we give this finite training data set. Can we actually learn a appropriate form from of phi? And also we want to estimate alpha. From phi and alpha, as I mentioned, they can give us the physical insights and interpretation. And especially we are very interested in if we collect the data from very short time period, like the system didn't display the collective behavior, we would like to know whether actually we can learn the phi and alpha well, such that these estimators can make predictions in a large time interval and to predict the collective behaviors. So these are the problem we are interested in. Please feel free if you have any questions. Okay, so here is some review of, okay.
So may I ask a question? So in the capital F, do you have any assumption about the capital F? Capital F is quite general.
Yeah, capital F is given the problem. Like here, for example, in this model, I want to use this type of parametric F to model the system. So I know it's like this form, but I don't know gamma and beta.
Yeah, but but I mean, so for your framework, as long as you have F has some expression, then you can do it. Is that what you mean?
Yeah, exactly. Yeah, okay, so thanks. We have a mixture like we don't assume any parametric form of phi because we don't know what's the canonical dictionary to model it, and but we know capital F. So later I will, when we see specific application, I will tell you why we do this in this way. Okay, so yeah, here is a summary of the previous work. In the previous work, actually, we work in the ideal setting. We propose some least square gradient matching. So here is the data set we collect. We have a good estimation about derivative data. So the idea is that, okay, because we know the physical knowledge, this phi is a radial kernel. So we use a very simple functions to approximate the phi. So you can see here, we fix on some interval, we use the piecewise constant to approximate the ground truth, which is given by phi. The idea is that we really want to find some candidate function whose velocity field match our training data. So you can see here, we actually want to find this coefficient Ci such that their velocity field are very close. And this method has several limitations. So first of all, it assumes that phi is only unknown term, so it doesn't have the flexibility in modeling F, capital F. Later, I will say why it's kind of like disadvantage in the practical applications. Another one is the model selection of phi. So suppose we give finite data, and so our challenge is that given for this finite data, how many partitions of this interval should we have? Like, I mean, when we want to actually minimize the approximation error given the finite data. So in theory, we have the asymptotic results. We know how, how to choose the number of intervals like scalable to the data, but we don't have exact answer. Still, like this is a challenging problem. And also the estimators don't extrapolate. For example, I compute the data, and this is the interval, the information interval. I didn't know any information beyond the interval. So this, and also we need a abundant trajectory data when ML, I mean, so typically here ML is large to make the method work well. So actually we test this kind of least square gradient matching in a lot of like systems. So here on the left panel is the true ground truth dynamics. On the right hand side is the prediction made by our estimators. So we apply this to the gravitation dynamics to differential meaning. So this is phototaxi, and this is the anticipation dynamics. It works well, but has the method has the limitations as I mentioned, and so here, the new challenge in our problem is that we want to do the joint inference of alpha and the phi. This has some practical advantage when we really face with the real world data, and it involves non-trivial like separation of the non-interaction force and interaction force from the dynamic data. And in particular, this capital F can depend nonlinearly with respect to alpha, like the example we have seen, the opinion dynamics. So this brings the nonlinearity in terms of inverse problem. And we don't know the parametric form of phi. So we really don't know which dictionary. So we want to do in a fully non-parametric sense. And also we are, I mean, in this research, our target is that when ML is small with some random effects. So in this case, somehow the unscientific quantification is very useful. So we really want to find some method that can address this problem as well as give us the unscientific quantification. So if you look at literature in machine learning, so we find out actually there's a method called based on the Gaussian process regression, and it has been applied to the data-driven discovery of dynamic systems. Here I would like to give the definition. So the definition is really simple. So we have Gaussian process is a stochastic process, and so here they say it's an abuse of notation. So have xt, and you have I mean this t is a continuous index set. It is a Gaussian process. If every finite set of time index t1 tk you evaluate this stochastic process, it's going to be a multivariable Gaussian. So in the literature, this Gaussian process regression has been employed a lot in the statistics and computer science community. The majority of work has been done in the parameter estimation. So they have some unknown parameters and they would like to estimate. They typically model the state variables as Gaussian process. And there's a lot of excellent work recently, and you can find a relevant reference in these papers. And in the literature of non-parametric estimation, and people don't want to assume any parametric form on the unknown function. So typically, either it can model the right-hand side function as a Gaussian process, or as well as data variable as Gaussian process. But later I will explain, and actually it's cursed by dimensionality. So here are two papers. One is for the ODE, and one is from PDE. So here the PDE. It seems to me it's quite natural because we don't know the parametric form of PDE in a lot of times. So we can model this function, the solution, as a Gaussian process, and it works very well. And okay, so inspired by this relevant like approach, we are actually trying to use the Gaussian process to tackle our problem. So our like observation is that here we do have a system which whose dimension is b times n. However, the interaction phi is only one b function. We really don't want to model some high dimensional object as a Gaussian process. We want to actually model low dimensional object as Gaussian process. So we actually model this phi as a Gaussian process. This is a mean is 0, and its covariance is given by some kernel. You may know about the Gaussian kernel, exponential kernel. So you have a kernel, and then you have some hyperparameter theta to model the length, scale, or amplitude of this kernel. And once you choose this phi as a Gaussian process, actually you give a probabilistic framework to the data. So the idea here is that because this x dot is linear with respect to phi, so if you model phi as a Gaussian process, this x dot is also a Gaussian process. Given this observation data, you can actually compute the maximum likelihood from this data. And suppose now you don't know this alpha, you also want to train this theta, and you don't know the random effects. So what you want to do is, okay, I want to choose this set of parameters that maximize this probability that I send the data. So what we do is we initialize some parameters here, and we solve an optimization problem to figure out this alpha, theta, and sigma square from the training data from a small set of training data. And here is a equivalent optimization form. So this first form is for the data fitting purpose. And the second form is kind of the regularization to on the model. Like so this is like trade-off between the data fit and the regularization on the model complexity. And once we finish this, we actually get an estimate of alpha and a theta. So this theta gave us the actually data-driven basis and also sigma square. And once we obtain all the information, we are able to compute the interaction force Fvx. And now the key observation is that the joint distribution of phi and Fc is still Gaussian. And now you want to predict the value of phi on a new location R star. So you can actually derive a closed formula to do this. And this is a posterior mean for the posterior distribution of phi. And this is variance can give us a uncertainty quantification. And why we use the Gaussian process regression? And in fact, Gaussian process regression, if we perform in a naive way, is known to be very, very computationally expensive. You can see here, this kernel matrix is of the large size, is NDML cubed. And so in the literature, there's a lot of work trying to accelerate the method. But still, people, even like the practitioners, choose to use Gaussian process because it really works well when the data are scarce and noisy, and it has a natural and certain quantification scheme. And also in our setting, it gives us a flexible model selection. It do the joint inference, and also it choose a data-driven basis. So that's how to actually tune this parameter theta. So later I will present an example to illustrate this advantage. And also we observe that the estimators do extrapolate. Maybe our interpretation is that they know the underlying smoothness of the kernel. Okay, so later I'm going to show you two synthetic examples. The purpose is they work. And here is the 1D opinion dynamics. It's a 10-dimensional dynamic system. Yeah, do you have any questions?
So may I ask a question in your previous slides? So in the training part, right? So so do you need to solve the forward part? So when you do the optimization, right? When you say when you do the gradient descent, right? You fix alpha theta.
Yes, we do gradient descent. Yes.
You fix alpha theta and the sigma square. For that, fix the parameter of your dynamics. Do you need to solve the ODE?
No, we don't, because we assume we have a derivative data from the ODE. So this x are observations of this x and x dot actually. So this y is x dot and x. So we don't need to solve ODE again.
Wait, but so in the training data, I understand you have x dot.
Okay. So let me understand your question. So this when we obtain the training data, we need to solve the ODE.
Yeah, for But I'm thinking about when you do the optimization, right? Because when you adjust those parameters alpha, theta, and the sigma square, that I give you a current estimation of alpha, theta, and the theta square. You need to see whether the solution of the ODE match your training data or not, right? So you don't.
Yeah. So here we don't solve the ODE. We see some relevant work they really do solve the ODE, but here we don't solve the ODE because we assume this x dot and xi dot are observed in
But then how do you
in
control?
our training
How
data.
do you use the parameter alpha theta to control the dynamic system? I mean, you need to feedback the choice of the parameters.
Okay. Yeah. Let me explain. So this x dot and xi dot are generated from dynamic system with true alpha and a true sigma square. And so now we actually use that dynamic system to give us training data. Now, suppose I don't know the training data. I would like to, suppose I don't know the hyperparameters. I would like to do the parameter estimations from the training data. So in terms of this optimization, all this capital X and capital Y from the training data. I don't need to solve the ODE again in terms of solving this optimization problem.
I see, but the part I'm still not 100% understand is when you give the parameter alpha theta, you need to treat the dynamic system, produce the dynamic path.
Exactly.
Say this path match to, but you don't. But you said you don't.
We don't. Yeah, we don't. We don't.
Sorry, hi, this is Peter. I mean, if I understand.
Hello.
Hi. If my understanding is essentially how you're working with this, you're essentially treating the differential equation as a mapping from state to a rate of change or a flow, right? And there's nothing else about the fact that it comes with a differential equation that you care about, right? So once and for all, you know, there's some, you know, black box that spat out this data, and from the data you observe the x doubled, you essentially, you know, can infer these derivatives and x dot, and you're just trying to fit a relationship to this data, right? So there's no point in trying to rerun the model based on, you know, your hypothesized versions of alpha and theta, right?
Sure. But,
yes, that's true.
Sure. But somehow you need to have some relation between the parameter and also the solution, right? No.
Yeah, let me actually explain. So the dynamic constraints is included in this covariance matrix KFC.
Okay.
Yeah, KFC here. So in this way, actually, we incorporate this dynamic constraints because when we actually model this phi as a Gaussian process, you already got xi dot as Gaussian process. You are able to compute the covariance and of the Gaussian process. And in this step, we need to use the ODE to incorporate this in like Gaussian process for xi dot. That's how actually we derive the formula for this maximum magnitude.
Oh, I see. So you sort of, in some senses, you're using Gaussian process to represent the solution of your ODE.
It's not ODE, it's like for the
dynamics
acceleration data. Yeah, exactly.
Sure.
Yeah,
okay,
exactly.
Okay.
Exactly.
That's the relation between this. Okay, thanks.
Exactly. Yeah. Now I understand your question. Okay, yeah. So here is different.
Sorry, just to clarify once more, just to be clear, you're really essentially trying to fit the second derivative as a function of state. You're not trying to like fit the whole solution as a function of state, right?
No, yeah, I model this phi as a Gaussian process. So you can see xi dot is a function about a phi. So that's why xi dot is a Gaussian process, not the state variable. But the state variable can be do the double integration about xi dot. So it's also a Gaussian process, but we don't use that information actually. We use only xi dot because it's available in our training data.
I see.
Yeah, hope it's clear.
I see. But there exists some approach. Say I incorporate it with the forward step solvers and do this.
Yeah, I think so. Yeah, that's true. Yeah, because in the work, I believe they don't assume they observe this xi dot and xi dot. They want to do fully noisy position data. So that's actually some work I cited in the previous slide. Yeah, they need to do forward like simulation. So here, I'm so I have the like derivative data, so this can simplify the approach.
I see. Thanks.
Yeah, thank you.
So is the key have to do with how finely sampled the data is? So if it's finely sampled, then you have a reasonable chance to estimate derivatives. But if it's coarsely sampled, then you can't use this approach.
Yeah, if it's coarsely sampled, I cannot actually estimate the derivative data in an accurate way. So this is a very like challenging in general, like for a lot of methods. Like if you want to, if you have very low frequency samples, how to do it? There's not universal good way to tackle this problem, especially in the context of complex dynamic system. Some method work, but if you apply for other system, it didn't work. Yeah.
Thanks.
Yeah.
Good, thanks.
That's a very good point. Yeah. Yeah, here below, I want to show like some examples, synthetic examples to test whether this approach work or not. So here is a 1D open dynamics. So this is the data. We have m equal to 3. So collect from 3 trajectories at l equal to 4. So this noise equal to 0. So you can see it works. So this is a black curve. It's a ground truth. And this blue curve is the posterior mean. And the pink band is the oscillating band, like we take the 2 times the standard deviation. And so of course we can increase data and we can consider different. So all it works very well. Even in the, I mean, here is an ideal noise model. So even in the like the noise equal to 0.5, the variance equal to 0.5, you can see we can do very good prediction and as well as generalization to the system. So this is on the training data. This is on the totally new data. So for testing purpose, and for, I mean, we find out actually for this alpha, this is a non-convex optimization problem, but somehow no matter how, I mean, we choose this initialization in a reasonable large region, somehow it can always return the good solution for this alpha, and as well as for the phi-hat in the big noise setting, we still achieve satisfactory performance. And this is the result for the 2D phase meaning dynamics. So this is 20-dimensional systems, and we need to figure out this alpha and beta. So you can see we choose 3 like snapshots. As long as we have accurate data, even this is 20-dimensional system, it works very well. And for both the kernel learning and as well as the prediction on the collective patterns. So this blue dots actually shows the training time interval and the prediction time interval. So you can see that really a lot of things happening, like this meaning pattern. We can predict the meaning pattern very well. And this, if we increase data, you can see some improvement in the performance. Yeah. So also for the noise, and it all work very well. And also we do comparison with our previous method. Suppose we know this alpha, like we only want to focus on the kernel, learning the kernel. So as I mentioned, like given the final data set here, we choose L equal to 5, a 5 agent system, ML is 5 and 6. So really, like given us a final data, how to choose the dimension in the previous work, we use the piecewise polynomials to approximate the phi. Really the problem is how to choose the dimension. So we range, we take a range from 10 to the 100 and with a gap 10 and try to figure out what's the best performance for the previous method. And here we use a Gaussian process. It automatically gives us a data-driven basis. So we actually compare their performance. You can see either in the noisy case or noise-free case and noisy case, all methods perform better than the previous method. And especially you can see some interesting phenomenon. And here we added some noise here, 0.01, and somehow the kernel learning is can be better than the noise-free case. So later we'll derive theory. Actually, this noise can be viewed as a regularization in this corresponding inverse problem. So it does help in terms of reconstruction. And now we also compare with some other well-established methods. So the Sandy. So this is a system with 5 agents, and we use our method. We incorporate this ODE model, and we know it very well. If we actually only treat it as a high dimensional function, for example, we want to use Sandy algorithm, we treat each row independently. We use the polynomial or sine cosine function to find a sparse solution for each row and trying to predict the dynamics. You can see it works very bad. And here is the neural networks. Especially neural networks, they don't have an advantage when the training data set is very small. And so here the take-home message is that once you know some physical information, and we have to incorporate this physics into the machine learning models. Otherwise, it's very, very important just from these numerical examples. So next, I want to make a summary from the synthetic example, the match our assumption on the data. So you can see that accurate. We can actually do the accurate parameter estimation and the recovery of the intention kernels from a small amount of noisy observation data. As I mentioned, one limitation is that we do need access to the derivative data like velocity and acceleration. And also the uncertainty band is small and regions covered by this pairwise distance. So here I forgot to mention. So this green histogram actually are the distribution of the pairwise distance I computed from training data. So these are kind of learning information interval. So before we actually just construct basis in this range. Somehow it doesn't extrapolate, but you can see here in the Gaussian process learning, even in the range outside this information interval, we can also approximate this field well, and this actually also support this non-time prediction, and also it has accurate prediction of various collective behaviors. So this uncertainty band actually is small in the synthetic example, can give us a lot of inspiration in the real data example, which I show below. So here we take a data set which is in Cousin's paper in 2010. So this is a data with 50 fishes, and it displays the flocking behavior. So here we want to fit the data with a Cuker-Smale model with Rayleigh type friction force, which is given here. We have kappa and p to fit. So first of all, I mean, we are not an expert in the domain, so we don't know which kappa and p to choose. So we choose kappa, for example, equal to 1, p equal to 1. So we use the method trying to find the best phi, trying to incorporate data and make the prediction. So this is what we did. Actually, this is the kernel. So you can see from the trajectory prediction, yeah, it predicts flocking behavior very well, but not satisfactory. You can see the real data is not exact flocking. So this means that somehow this non-collective force is also important in determining the dynamic behavior. So then we do the joint inference of alpha and the intention kernel. So you can see here we do learn a kernel with a large uncertainty band. So this actually tells us this has a model mismatch problem. So our model maybe are too simplified for this real world dynamics. And it's not, I mean, you can see the uncertainty band is very big, even in the range, in the interval covered by this pairwise distance. But if we use the posterior mean to predict dynamics, you can see actually they match the data very well. But this uncertainty band suggests that there may be other dynamic systems can also do the job. So we actually use the Sandy and also neural networks trying to fit the dynamics. So you can see that, yeah, I mean, it achieved comparable performance in terms of trajectory prediction. But we want to emphasize here, we really figure out some model with a very good physical interpretation. Like we know how this collective behavior are derived from the pairwise distance, for example, in the system. But for the Sandy and the neural network, it's more like some black box, and you don't know how agents interact to produce the collective behaviors. So this is some real data example we've tried. Okay, I don't have many time for the theory part, but really this empirical performance motivates us to think, okay, why this approach can work, and understand the limitation of the approach as well. So here we really take the perspective from the inverse problem. I know many audience are working the inverse problem, and here let's say we consider the simplified first order system. We have xt, we have x dot t. We really use this f as a linear operator, mapping this interaction kernel phi to the vector value function. So you can think xt is this x dot t in the image. You can take xt is the image, and x dot is some our samples via some linear operator. Really the inverse problem is that we have the Lloyd data of x dot and go to infer phi. And the difference is that in all settings we have a linear operator given by f incorporating the underlying physics. Not like the analog example in image, for example, this A can be a blurring operator, like it's a convolution type operator. But here we have a specific operator F incorporating the physics. So the question is that, okay, given the finite data is free, and like can we recover phi? And I mean, how does this posterior mean convert to phi? This actually answers the sample complexity question. Like if it is, then in which norm, what is the rate of convergence? So using the language inverse problem, what's the reconstruction error once you have finite data? How to choose, say, the hyperparameters in the learning. So our work is exactly like from this point of view, we derive a rigorous operator theory-based framework for the quantitative analysis. So we answer the question for the identifiability, and we show actually under some conditions, this problem is equivalent to the 1D kernel ridge regression. So it's called the Tiago of regularization in the inverse problem. So this actually implies the scalability of our data set. We don't need that many data set to deal with a problem in ND. So it could be as easy as a 1D problem. And we also show how to tune this prior to satisfy the optimal rate for phi satisfying the holder source condition. So I don't have many time for this part. So I'm going to actually present the theory in a brief way. So first of all, we make a connection with the kernel ridge regression. So if we assign some phi with a Gaussian process, say 0 and k tilde, and the k tilde here is sigma is the noise, over m is the number of trajectories, n is the number of agents, l is the number of time snapshots, and lambda is some like parameters, and the k is a Morse kernel, like it can generate a reproducible kernel Hilbert space. Once we assign this type of a prior, the posterior mean phi m bar given in our Gaussian process actually coincides with the solution with the kernel ridge regression. So you can see that here in the first order setting, we have the noisy observation of velocity, and this xml is the position data, and the psi is some like is a candidate function in this reproducible kernel Hilbert space. So here is L2 term, and this is a regularization term on the norm of this of the function phi. So the solution are the same. So it means actually we can study the posterior mean of estimator using this connection with the kernel ridge regression. And also we address identifiability from the point of view of statistic inverse problem. We analyze when this problem is doable, when the data is infinite. So motivated by this, we introduce several measures. So these measures will actually give us function space to talk about the convergence. So here rho x is the Dirac measure at these positions, and rho TL is a pairwise distance distribution. We have seen a histogram in the previous figure. We see this system satisfy the coercivity condition if the following is true. So this is the energy of the system. You want to be bounded below by this this norm induced by this rho TL, and this coercivity condition, we show that this linear operator f star f is equivalent to the canonical operator, like this is canonical operator for the 1D kernel ridge regression. Because this operator is kind of unique, like have the well posedness, because this is equivalent, so our problem is also well posed. And we also verify that this coercivity condition is true when L equal to 1. For example, we have a finite dimensional edge case space, and where the Morse kernel case smooth, and whenever this edge case is a subspace of the Sobolev space W2S when S bigger than 1/2. As long as have this, actually the coercivity condition is true, and we do have identifiability. And based on this assumption, we are able to prove the reconstruction error. Like if we given the data collected from M trajectories, and then we choose this lambda to the prior, according to this number. So it's also not an exact number, it's a scale size as this number. Then this reconstruction error will, with high probability, the decay rate is like this. So this gamma actually coming from this condition. This condition is a little bit abstract. It's called the holder source condition in the inverse problem. And this is kind of optimal rate. So I will make some like brief comments. So in our bound, it's really crucial to have this condition number, CHK bigger than 0. Otherwise, our bound is meaningless. And the coercivity constant is, in fact, depends on the number of agents, N, L, mu0, and HK. In our paper, we consider both N, L, and fixed, and we proved that CHK is positive, even can be independent of N in the case of L equal to 1, once we choose some initial conditions. And also the convergence in the HK norm can imply the convergence in the CS norm, which is provide the kernel case is sufficiently smooth. One can use the standard dynamic system techniques to obtain the L infinity bound for the trajectory prediction. And also the convergence rate in M coincides with the optimal rate achieved in the classical 1D kernel-rich regression setting. And also the convergence rate is done for all Mosaic kernels. So in the literature, once you know more information about the Mosaic kernels, like the eigenvalue decay property or eigenfunction is bounded in L infinity norm, you can derive much accurate rate. And because we have the equivalence between our operators with the classical operators, and this can give us bridge to derive more exact rate for kernels with more specific properties. And you can, from this result, actually this proves the scalability of M and optimality of the approach. So no matter what kind of approach you use, and if we view M as an effective sample size, this is already optimal in the minimax sense. Okay, so this, of course, this is only like a very preliminary investigation of our method. So we don't do any acceleration trick, because this one difficulty is that this is a highly coupled dynamic system. Some assumption made in the acceleration method before is not true for our system. We did not try a good, we haven't found a method that can work very well using the current literature. And also we have like assumption derivative data. How about we only have noisy position data? Can we actually using the Gaussian process regression to deal with this case? And also this is low frequency data, as I think the Peter just mentioned, like you have a large time gaps and how to do this. So these are very interesting problem to explore in the future. So that's kind of some open questions regarding to the identifiability. I don't have much time, so basically for us to compute to tackle this problem is really a problem in analysis. Like given the initial condition, we need to compute whether this inequality is true. Then it suffices to know whether this kernel is positive definite. So we borrow a lot of ideas from the density theorems in sampling and approximation theory and trying to tackle the problem. And for the stochastic system, and we can do more, because sometimes we know, for example, the solution to the OU process and where the system is orthogonal. This kind of information can give us the closed formula close the formula for this kind of inequality, and which allow us to do some analysis. But in general, we don't know how to tackle this problem. So, so thank you for your attention. So this is another real data set, like for fishing, the fishing miming. And feel free to ask me any questions after talk. Yeah, thank you.
Thanks, Jui, for the very nice talk. Any questions so far?